Hi again. I hope you're having a great day so far. And thank you for attending today's session, EREF Science Session on Weighing the Options, Current Strategies for Managing PFAS in Leachate with Dr. Stephanie Bolyard, Research and Scholarships Program Manager at EREF. My name is Liz Bothwell, and I'm Head of Content and Marketing for Waste 360. And I hope you're enjoying these science sessions as much as I am. We have another one coming up. It's called Rock Solid, Evaluating Solidification of PFAS in RO Concentrate. And that is happening on Thursday, March 11th, between 1 and 2. And we will be sending a note about that out around March 1st. So please look for that. And we have to do a big shout out to our sponsors for this science session. Without them, it wouldn't be possible. So thank you to Civil and Environmental Consultants, Golder Associates, Labella Associates, and Republic Services. And we're all used to these housekeeping items as we're doing more and more Zooms and webinars. Just reminding you that you've all been muted. If you have any questions for Stephanie, please use the chat function, and the questions will be addressed toward the end of the session. And we will have the PowerPoint presentation is there for you, so you can go ahead and download that through the handout section, and that's in the window. If you have any technical issues, we know they sometimes happen, just use the chat function and someone from the EREF staff will help you. And last but not least, if you would like a certificate of attendance, just make sure you attend the whole webinar, and a link to the certificate, an evaluation survey, and the recording of this science session will be sent to you next week, March 1st. So let's get to it. I'd love to introduce our esteemed speaker. Welcome, Stephanie. So this is Dr. Stephanie Bolyard. She is the Research and Scholarships Program Manager for EREF. She has a PhD and MS in Environmental Engineering from the University of Central Florida and a BS in Chemistry from the University of Florida. She has 12 years of academic and professional experience in various fields, including solid waste management, domestic wastewater permitting, and environmental compliance. She's published numerous papers in the area of post-closure care, leachate treatment, PFAS management, and emerging contaminants in leachate. So as you can see, Stephanie is the ideal person to talk about PFAS today. And PFAS, as many of you probably know, these man-made chemicals have given us convenience for decades, and they're everywhere. That nonstick pan, that stain-resistant couch, that waterproof clothing all contain PFAS. Its convenience and usefulness have led to the chemicals being found everywhere, from our water supply and our soil to even our blood supply, and of course, landfills. And that's what brings us here today. Stephanie will share the science behind PFAS and leachate, the EPA's interim guidance, the knowledge gaps that exist, treatment technologies, and so much more. So Stephanie, let's get started. Could you please talk more about why we see PFAS in leachate if the landfills are not the actual producers of PFAS?
Yeah. Well, Liz, as you already had briefly highlighted, PFAS is everywhere. It's in our daily lives. It's in places that we almost never imagine PFAS to be. PFAS was first invented in 1930s. It was PTFE, it's Teflon, that non-stick coating in that pan that we love and use. It's why we have that perfectly cooked egg at breakfast. And it, from that point on, has been in Scotch Guard. It's been in our waterproof clothing. And it's not just in our consumer products, but it's in the manufacturing of items. So it's in industrial processes. It's even in our food wrappers. And it's to the point now where we're finding it in pristine environments where we're not having the human impact and pointing to why we would find those PFAS compounds in those pristine environments like the Arctic, showing that they are mobile. And one of the things that when we're looking at the PFAS production and manufacturing and then ultimate use cycle, we would see that landfills are receivers of waste, such as the consumer products that we use on our daily basis. Landfills are permitted to manage our waste daily. The thing to keep in mind is that we've spent decades as engineers and scientists and geologists to design landfills that are containing and protecting human health and the environment from the waste materials that go to landfills. They have well-engineered liner systems. They manage leachate, gas, those types of emission from those facilities. But at the end of the day, they are permitted and they ultimately they take those wastes, and those wastes now have PFAS in them. And we are dealing with that. And as I had said, in 1930, the first PFAS compound, PTFE, was produced. But now to date, we have over 4,600 PFAS compounds that are registered and considered PFAS.
So I know that the EPA has issued interim guidance. Steph, could you give an overview of what it says, what it's focused on, and any key elements of the guidance that will help us?
So the interim PFAS guidance that was put out to EPA for public comments covers both the destruction and disposal of PFAS containing waste materials. In their guidance, they looked at the available science on the types of materials that would contain PFAS and what type of disposal and treatment options are available, and what information we have on the efficacy of those disposal options to manage those wastes, as well as what treatment options are available for those wastes, and also what the best suitable option is to manage those specific wastes. So based on the review of the currently available literature, the interim recommendations from EPA outlines 3 different management options that are outlined as underground injection control, landfilling, and thermal treatment options. One thing that they also outlined and recognized is that not all of these management options are suited for solid, liquid, and gas waste. So keeping in mind that underground injection control they recommend is suited for liquid waste. Liquid waste, for example, would be leachate, wastewater. Landfills would be solid waste materials. So that could be biosolids, wastewater, drinking water sludges, contaminated soils, consumer waste. And then looking at thermal conversion processes, they deem that those would be suitable potentially to treat both solid, liquid, and gas phase waste.
What do you see are the limitations in these primary management pathways?
So some of the things that we do know revolving around these pathways, as well as their limitations, is that underground injection control has been used to manage wastewaters in the past, as well as disposal for leachate. But a few of the limitations that are recognized in the interim guidance is, as I mentioned before, it is suitable only for liquid waste. In addition, there are very specific geological needs to have a installation of a Class 1 well, and that would translate to only specific geographical locations where that would be suitable. In addition, we don't have a vast network of those types of wells. And then if you wanted to dispose of your waste at a underground injection control well, odds are you would have a hefty transportation cost to tack on to that disposal cost as well. So those are some of the limitations that were highlighted revolving around that type of management options. Now looking to landfills, this is going to be for solid materials. And as we know, we have a lot of science out there and decades of engineering experience to show that landfills are effective at managing municipal solid waste. Now looking at these man-made forever chemicals, some of the knowledge gaps, is probably a better way to put it, is really just understanding if the existing liners are able to manage and prevent the migration of PFAS to groundwater. That's actually currently being studied under an EREF project right now. Understanding existing leachate collection systems to collect that leachate that would contain PFAS, and the treatment mechanisms that are going to be effective at treating leachate containing PFAS. Will gas collection, is PFAS going to be in the gas wells, things like that. And then in terms of thermal treatment processes, some of the limitations that we'll cover in some additional details is just whether or not the current treatment schemes are going to be effective and able to destruct PFAS. So is time, temperature, and turbulence enough to destruct PFAS containing waste materials in that type of treatment method?
Now, I think a question we all have is why is PFAS so challenging to treat in leachate?
So thinking about PFAS, one of the things I think about is, why is it so stubborn? And it was looking at kind of the basics, kind of coming back down to the fundamentals of PFAS, is it all comes down to the carbon-fluorine bond. So if you were to Google this, that's the very first thing that scientists are they're going to explain to you about PFAS. And the carbon-fluorine bond is really a double-edged sword. It is why we have these positives, why we have these conveniences in our life, the nonstick pans, the stain-resistant carpets, the waterproof shirts. But it is also why, and as engineers and scientists, we have these challenges of tracking PFAS in the environment, analyzing it, treating it, comes down to the carbon-fluorine bond. So explaining that really comes down to electronegativity. Carbon-fluorine bond is the strongest single bond that is possible in the field of organic chemistry. And the reason why is that fluorine is the most electronegative element on the periodic table. And one way to explain electronegativity is a magnet. Is it a magnet to attract electrons? And when we would compare the bond strength, how tightly does carbon and fluorine hold on to electrons when they come together, really comes down to the relative differences in electronegativity of those two atoms. So that really just makes fluorine so unique, is that it's such a strong magnet to those electrons when it comes into contact with carbon, that it pulls it away from carbon, holds onto it tightly, and therefore has a very strong bond. But when we look at the comparison of the bond strength, so basically the energy needed to overcome that bond between, let's say, carbon and hydrogen to carbon and fluorine, we see about a 17% increase in that bond strength. And then if we were to compare that carbon and fluorine to other traditional bonds that we're used to seeing, like carbon and oxygen, carbon and nitrogen, we can see that even comparing it to that, carbon and fluorine is even higher than those more traditional bonds that we're seeing.
Well, thank you. That magnet image makes it so clear. So that's a great image to look at. Thank you for that. And then, so Steph, what types of treatment technologies are currently available to really treat PFAS?
So before we think about really the treatment technologies, it's helpful to look at the mechanisms. Because PFAS is so unique and that bond is so strong, and we ideally want to, instead of thinking about treatment as a black box, what comes in, what goes out, we really want to know what's going on in that treatment process to make sure what's coming out is not containing PFAS, or we're adequately controlling PFAS and not creating other PFAS compounds. You really need to take a look at the different types of mechanisms that are possible in the area of leachate treatment. So one of the first mechanisms to think about is destruction, because as we highlighted in the EPA interim guidance, as they recommend destruction in terms of treatment, is destruction ideally is taking the example of, let's say, a PFOA compound, treating it to the point of where we only have fluorine and CO2 left over. One of the challenges with destruction methods of PFAS is that there is some uncertainty as to whether or not the destruction is 100%, so it's complete. If it's not complete, we would say it's partial destruction. And we might not have PFOA anymore, we might have a shorter chain compound that's still considered a PFAS that we would need to be managing. Another treatment mechanism that is used is sorption. So that is a way of taking a solid material and using the affinity for a contaminant like PFAS to adhere, so adding to the surface of that solid material and taking it out of solution as a way of treatment. And then another form of treatment is filtration. And filtration works similarly like you would think about when you're making coffee in the morning and you have to use that filter to make your coffee, because you're going to be adding your coffee grounds, and we don't want coffee grounds in our coffee in the morning. So that filter works by having pore sizes that are smaller than those coffee grounds. We run water through it and we get our coffee out the bottom in our cup, and we have our coffee grounds that we dispose of. Well, filtration works on a similar mechanism where if we know the size of the contaminant we want to remove from our leachate, we can then pick a membrane, in this example, that has pore sizes smaller than that contaminant. Therefore, it would block the contaminant from passing through that membrane. And then we would have a clean source of liquid on the other side that would not contain that contaminant.
So Steph, which of these technologies are available today?
So looking at what we call off-the-shelf technologies that we could say to an industry stakeholder that needed to remove PFAS at their landfill, what they could use right now. The first two technologies that would come to mind would be that sorption and filtration mechanism that I had mentioned. Granular activated carbon and reverse osmosis are both two treatment technologies that have been shown to be effective at removing 90% or more of PFAS, even in leachate. So thinking about granular activated carbon, as I had mentioned before, that's a solid material that has an affinity for an organic contaminant to stick to the surface of that granular activated carbon. So in this example, PFAS would stick to granular activated carbon. But as you can imagine, that solid surface only has so much ability to retain PFAS on that surface. So at some point, you are going to have to change out that granular activated carbon and either replace it with fresh granular activated carbon or regenerate it. But there's still some science out there as to whether or not that is an effective method, and that regenerated carbon is as effective as virgin carbon. But one of the things to consider with sorption is that you're taking PFAS from a liquid waste stream and putting it onto a solid waste stream, and you're still going to need to determine a way to manage that solid waste stream. In this example, granular activated carbon containing a concentrated amount of PFAS. Flipping over to filtration, reverse osmosis, very effective method based on the literature in terms of removing 90% or more of PFAS. But one thing to keep in mind is that looking at the example of leachate, you're going to treat leachate, remove PFAS, but you're going to have a concentrated waste stream known as a RO concentrate that is going to actually have more PFAS in that leachate concentrate than leachate alone. And one of the questions is going to be is, okay, now how do I manage that leachate concentrate? And one of the interesting and unique novel ways to manage that is through a method of solidification stabilization, which is going to retain that PFAS in a solid matrix. And that is actually going to be a focus of our next science session, Rock Solid, that will cover the novel ways to combat dealing with RO concentrate and PFAS, which is exciting.
That is exciting. And then talking specifically about treatment, what is EPA's recommendation for PFAS management, and are there still knowledge gaps related to these technologies that we need to talk about?
So looking at the specific treatment recommendations that are focused on destruction, and those thermal treatment recommendations that are outlined revolve around thermal conversion facilities. And some examples of those are waste energy facilities, hazardous waste incinerators, thermal oxidizers, sewage sludge incinerators, some existing commercial facilities that are already effectively managing waste streams via these thermal conversion methods. But when we're looking specifically now at waste materials that contain PFAS, some of the knowledge gaps that are still out there revolving around these thermal conversion technologies look at their operations of time, temperature, and turbulence. Those are going to be the quintessential terms that if you talk to anyone in the field of thermal conversion processes, that's going to be their go-to to explain the operation of those facilities. These operational parameters are not specific to all, let's say, waste energy facilities. It's going to depend on the characteristics of the feedstock coming into that facility that's going to dictate the temperature, the time of that waste material being in that, let's say, incinerator, to make sure that there is enough time for that material to be fully destructed. And then we have turbulence that is also going to impact that operational condition. So in terms of understanding how much time, turbulence, and temperature is needed to destruct PFAS, there are only a handful of papers, I think about 3 or 4, that have shown some promise at temperatures above 1,000 degrees Celsius, and a few seconds residence time might be sufficient. But there's still studies that need to be taking place to understand that. Now, understanding the processes are going to be important, because one of the things that need to be understood is whether or not these various conditions will promote the formations of products of incomplete combustion. So thinking back to when I had mentioned the difference between complete destruction and partial destruction, this is how we would explain the products of incomplete combustion. If we do not 100% destruct, let's say PFOA, and it produces a shorter chain, a smaller PFAS compound, that's going to be termed a product of incomplete combustion. And that's going to be a PFAS compound that we're now going to have to manage in the air pollution control portion of a thermal treatment facility. Those products could reform back into another longer chain PFAS compound. They could produce the formation of HF. Another unknown is how PFAS will go through air pollution control units. And those air pollution control units could produce some type of waste stream that needs to be managed. Similarly with ash, is PFAS going to be transferred to the fly ash and bottom ash and need to be managed?
So do you think there are opportunities for scientists and research to help fill these knowledge gaps and really advance the destruction treatments specifically for leachate management?
There certainly is. These treatment mechanisms and treatment facilities that we recommended, the interim guidance does highlight that they can treat solid, liquid, and gas streams. Looking at leachate and thinking about the, let's say, thermodynamics and just the processes of time, temperature, and turbulence of these thermal conversion processes might not be ideal to treat leachate alone. So thinking at the literature and what's currently available that is considered a destruction methodology for leachate treatment, what comes to mind is what we would call a non-thermal destruction method, such as an advanced oxidation process. That is something along the lines of Fenton's reagent, ozone, UV treatment. These are very, very reactive, sometimes non-selective ways at treating conventional organics in leachate and have been highly successful in the literature. One of the things that scientists have found is that despite the ability for those processes to treat those conventional organic contaminants and those, let's say, typical bonds that I had highlighted earlier, they were not as effective at treating PFOA and PFAS in the literature. And one of the things that we would attribute that to is the strength of that bond. And in those processes, they utilize free radicals to destruct those compounds. So just like you would hear free radicals in the environment or free radicals in your body, like, we need antioxidants to combat those free radicals and oxidative stresses, right? Those free radicals are not good for organics either. They don't like their electrons being taken and they're not happy. Well, there needs to be ways to potentially find alternative oxidation processes or alternative destruction methods that are powerful enough to overcome that bond barrier to destruct PFAS.
So do you think there are other destruction technologies on the horizon?
Yeah, there is a plethora of scientific literature out there that have found ways, very novel ways, to overcome that bond barrier and I'd say outsmart the carbon-fluorine bond by adding more power and more strength to those free radicals and those oxidation processes. Some of the technologies that I'd like to briefly talk about today do cover some non-thermal and some thermal destruction methods that have been specifically applied to leachate treatment and have shown some promise to successfully removing PFAS. The first treatment methodology, and it was highlighted in the EPA interim guidance, is called supercritical water oxidation. And I'm sure we all remember at some point in our studies where we learned about the phases that water matter can exist: solid, liquid, and vapor. Well, scientists have found that if we take a liquid at a specific temperature and pressure, we can reach a very special state known as a supercritical state. It's not a water, it's not a liquid, it's not a vapor, it's not a solid, it's supercritical. And in order to reach that state, we have to be at a temperature above 700 degrees Fahrenheit and at a very high pressure. And one way to translate a 250 bar pressure is imagine diving down 1.36 miles in the ocean. I think we all can remember diving down into an 8-foot pool or a 10-foot pool, and we hear our ears pop. So we can imagine the pressure of going that far down in the ocean. So very high temperatures and pressures. At those conditions, scientists have found that they can destruct organics to clean water, produce energy, and then produce CO2, which is a lower greenhouse gas emission. And they have been able to apply that process to leachate and remove PFAS, but they've also been able to apply that process to more concentrated streams, for example, sludges, and destruct PFAS. This is actually a focus of an EREF study right now, where they're looking at RO concentrate, which would be a great method to treat that concentrated waste stream containing PFAS in a destructive way to remove PFAS as well. And then some additional ways that scientists are adding additional power to that oxidation process that I had mentioned earlier is through some ways that are called electro-oxidation. There's a process called electrodischarge plasma, which is a very pretty process to look at because it looks like lightning in a reactor. And what's interesting about this process is scientists are using plasma as a free radical to destruct PFAS. And when I think about explaining plasma, I would think about, well, plasma, what do I hear that? It's a sci-fi movie. It's not just for sci-fi. But one of the ways that I would explain plasma is that when scientists add electricity to water, they form aqueous electrons that then will interact with PFAS and form PFAS radicals, will break down PFAS, and they have this complex reaction that can destruct PFAS. But one of the things that scientists have been able to use is, in a sense, use some of PFAS properties against them to actually bubble up PFAS to the surface and use this reaction to destruct PFAS. Another way that scientists have been able to use these advanced oxidation processes is through a electrochemical oxidation filtration process. This process is targeted more at shorter chain PFAS compounds, so in the range of about 4 to 6 carbon number. And the way that this reaction works is using electricity, so a DC current, and it is using an anode and cathode, which is something that you have in your battery and why a battery works. And they are able to run a current through the anode and cathode and facilitate that oxidation process. And one of the ways that they're able to overcome the power necessary to break that carbon-fluorine bond and treat PFAS is because they can control that power in that process and facilitate the formation of those free radicals and overcome that bond barrier and treat PFAS. So it's just really exciting to see how scientists are taking these, let's say, conventional processes that scientists have been using for decades to treat these contaminants that we've known how to treat for years. And although they're not working for these forever man-made chemicals, known as PFAS, they're finding novel and unique ways to make some alterations to them and find ways to overcome the lack of, in these examples, power necessary to destruct PFAS. So it's just really exciting to see how quickly scientists and researchers are coming together to address such a fast-moving challenge that we're dealing with today. So Liz, I've talked a lot about PFAS, thrown out a lot of information out there. What do you see as kind of the key takeaways from this discussion?
Thanks, Steph. You covered so much, and I love the way that you present information, because you present science in a way that's very accessible to people without a science background. So I need to thank you for that. And for me, the key takeaways have been, it's really clear that more research needs to be done in order to fill all of the knowledge gaps that we discussed. And I know that that's happening at EREF and will continue to happen. Also, the existing technologies that are out there are effective at treating PFAS, but our industry still needs strategies to really manage these residuals. And then another takeaway, I think, is exciting, and like you mentioned, there's a lot more innovation and technology on the horizon, and that's what's so great about our industry, right? This is a huge challenge for us, and something we haven't encountered before, but we're stepping up, and we will figure out a way and look for more innovation in order to help solve this big challenge. Did I do it justice, Steph?
Perfect. Perfect. I think
okay.
Just the focus on the science aspect, I think, is just so exciting when we're tackling issues like this. Just to see just the novelty and the creativity of just what's out there to look at these.
Definitely. There's so much. And I know we have questions from everyone out here, so let me get started, because I know they want to learn even more. Okay, so our first one, this is a good one. Are PFAS water soluble and biodegradable?
They are water soluble. That is one of the reasons why we do see them in the environment. But they are not biodegradable. There's research out there, and I think even some EPA reports that have shown that they are resistant to the conventional biological treatment methods, and that's why we're having to look into these advanced oxidation processes, chemical methods, thermal destruction. There is some literature out there on these super microbes that are very specific, that might be able to defluorinate and then make PFAS kind of unstable and kind of break apart that way. There is some limited information on maybe different fungal organisms that might be able to remove and break down PFAS, but overall it has been shown that biodegradation is not a primary pathway of treatment.
And then here's another good one. Do treatment methods that claim to destroy PFAS or PFOA actually destroy them? Or like you said, do they only convert them to some of those shorter chains that you discussed?
I think that one's a challenge to really break apart, because if we think about the PFAS compounds that we're trying to remove, a lot of the studies are looking specifically at, let's say, the efficiency of removing PFOA, and some of the ways they might understand the complete destruction is doing a mass balance of how much fluorine we'd expect to see after treatment. But since PFOA is so complex, and even looking at the pathway of complete destruction of PFOA, that in itself is just complex to show, that you would have to do a very complex kind of non-targeted analysis to just almost like throwing a bunch of darts at the board to understand like what's there. And just it's challenging because, as I had mentioned earlier, there's 4,600 different compounds. We don't know how each of those individually break down. But scientists are trying different mass balance approaches, looking at mass balance recovery, and trying to understand the 100% destruction aspect of these approaches.
Okay, thanks. And then how can owners differentiate between technologies that work in leachate versus in relatively clean water?
Well, I know that EPA has a nice, robust database of technologies that have been demonstrated to be effective at treating PFAS, and they do outline what type of matrix that they are suitable for. Definitely looking at the literature, those papers clearly will outline if they're going to be suitable for wastewater or leachate. Some of what I had shown, I had already mentioned that those are specifically looking at the treatment of PFAS and leachate, but there are definitely a number of papers out there that are looking at the effectiveness of removing PFAS from leachate. But granular activated carbon has successfully been applied, and reverse osmosis as well.
Okay, great. And I know we'll talk about that in the next one. But Steph, can you comment on the temperature that the current thermal treatment plants generally operate at?
Based on the literature and my understanding is it's above 1,000 degrees, and the residence time will vary. And according to, I think, the technology brief, that's basically kind of the minimum kind of starting temperature and conditions. But there's not a great body of knowledge out there on really what's required to fully destruct PFAS in this case to adequately say, yes, this is definitive temperature that's necessary.
Sure. Okay, that makes sense. And then this one's about the health effects. So this person's asking, PFAS is also found in bottled water, and we know there are effects on infants and pregnant women. Aside from leachate, could you tell us more about the current treatment process involved on the removal of PFAS in the surface or groundwater?
I say that's probably beyond the scope of this talk for sure. But looking at the literature and trying to understand, let's say, contaminated sources of drinking water, those are mainly going to be associated with industrial site, close to industrial facilities, or runoff from like AFFF, so the firefighting foam facilities. But some of the things that I had mentioned earlier, granular activated carbon, is a great polishing step after treatment. Reverse osmosis, those are going to be those processes that you're going to see implemented at those facilities. And EPA has set those guidelines of those limits that we need to stay into to avoid health effects. But one of the challenges that we do see with PFAS is a lot of the health studies have always said probable health effects. There aren't definitive health impacts, and those probable health effects have always been linked to individuals that have been in the DuPonts, the industrial facilities where they have had high concentrations exposure, not necessarily the exposures that we would see on our daily basis.
Okay. And this is another good question. Is energy consumption a consideration when treating PFAS?
I would say definitely the thermal aspect of things. I would say, thinking about a thermal conversion process, they are going to be generating energy, and that can be recovered to generate electricity, so that can definitely be an offset. But I'd say anything with treatment, there's always going to be a cost, and you have to weigh, the environmental implications, and it has to be managed in some form or fashion. But I think one of the encouraging aspects of our field is there's a lot of scientists out there that are looking at, net neutral in terms of energy balances. How can we engineer a process to where we might be putting energy in, but we want to get the same energy out, and it balances in the end. I think the same thing with the supercritical water oxidation. It can be a very energy intensive process, but it's also producing energy. So how can we balance that, or find more efficient ways to maybe use renewable energy sources?
Oh, those are good points. Let me see, we have another one. Does leachate typically require treatment to remove other contaminants prior to it treating for PFAS?
Yes. A lot of studies do suggest that depending on the type of treatment that you're doing to remove PFAS, so for example, if you're using that sorption process, there could be other contaminants that are going to want to adhere to that granular activated carbon. So you want to be careful, because if you want to remove PFAS via granular activated carbon and you have something else that's going to want to stick to that surface, you're going to want to remove that prior to removing PFAS. So that's one of the things that some engineers are looking at, is preferential removal of PFAS by trying to separate what different characteristics that might drive PFAS to want to go to one surface versus, let's say, organic, so humic acids that want to go to another surface. But I mean, typically leachate has high concentrations of organics, ammonia, color. Those are all things that can either be pre-treated prior to going to a wastewater treatment facility. But at the end of the day, it really just depends on what that owner operator picks for their treatment process. If it's RO, that's not something you're going to be as concerned about in terms relative to sorption, where you're going to have other things that are going to want to stick to that surface.
Sure. And I know you just mentioned this briefly, using granular activated carbon, as you said, generates solid waste covered in PFAS. So then is it disposed of in the landfill?
I am unsure about that, because I know that now that we understand more about what types of materials contain PFAS, there's going to be some landfills that are not going to want to take that, which makes it even more challenging to manage those wastes, which is one of the motivations of that solidification stabilization technique that will be discussed next week. But that's also a focus of EPA interim guidance, is recommending methodologies that they consider to be repositories, and that will actually retain those PFAS in those disposal options until we can find ways to, let's say, better to treat those PFAS instead of just retaining them in a repository. But thermal conversion can be an example of where you could manage that granular activated carbon. But that's something that would need to be evaluated. Landfills have been shown to be a sink, and if that's the case, then that could be potentially still a method, but there would need to be some research revolving around that to see if, okay, PFAS sticks, but is it going to unstick at some point?
Sure. Okay. And then the next question is about pre-treating as well. Do you think that leachate will need to be pre-treated prior to treatment with plasma or electrochemical technologies?
I think right now that project is just starting. So mechanistically, we're aware of how that works. I know that right now they've discovered different surfactants and ways to get PFAS up to the surface. They haven't necessarily identified a need to pre-treat, but definitely these questions are highlighting one of the challenges of dealing with leachate as a complex matrix. Is we're not like drinking water. It's not the only thing that we have to worry about. So that's definitely something that needs to be considered when looking at these treatment options.
Absolutely. And here's another one. Do you think that EPA or states will require landfills to remove PFAS from leachate before sending them, or refuse to take leachate in near future because of proven pass-through of PFAS?
That one's a challenging one to really address. I'm not going to take a stand on that. I'm just going to maybe do a food for thought. Remember that landfills produce, think about the production of leachate relative to the production of domestic wastewater and what we're flushing down our toilets and using every day. In my experience, landfills I've worked with might be discharging, less than 1% of leachate to a wastewater treatment plant relative to their flow. So if we think about that relative to what's in a wastewater treatment plant and then what's going out to surface water and pass through, a solid waste facility in a sense is a few orders of separation from any potential point of human exposure for drinking water. And as engineers, we don't like to talk about dilution. But what's important when we're talking about PFAS and treatment and exposure is we really need to understand what the relative exposure of these different aspects of management on a day-to-day basis.
Sure, and that's a challenge.
Mm-hmm.
Okay, here's another good one. What is the potential for PFAS to exit landfills in air emissions, flares, waste to energy, etc.?
Currently, there is not a what we call a standard method for measuring PFAS in landfill gas. And you might think that, oh, it's easy, but we need to trust our methods and we need to be able to validate those methods. So there is an EPA study right now that its goal is to develop and validate a method to measure PFAS. But what we see right now in the literature to try to understand what PFAS might be in landfill gas and its partitioning from solid to the gas phase has shown that PFAS that has an alcohol functional group are the ones that they're seeing in landfill gas. There has been only a handful of studies, like the University of Miami. I think there's a study in Germany and China that have looked at not necessarily landfill gas, but also air emissions around a landfill to see what types of PFAS compounds are there. So that science in itself is kind of in its infancy to try to understand what's coming out of the landfill. There is also science needed, and that was, I think, part of EREF's RFP is recognizing are the conditions in a flare, are those sufficient to oxidize PFAS compounds? So a similar example of what I explained as knowledge gaps for the thermal conversion processes would be similar to flares. Are those going to be enough to fully destruct PFAS, or are we going to have incomplete products coming out? So there's still knowledge gaps there that need to be filled to understand that.
Okay, thank you, Steph. And I know we're running out of time, so thank you, Stephanie, for all of your insights. It has been amazing. And I want to congratulate you on behalf of Waste 360 because you are one of our 40 under 40 award winners this year. And talking with you today just shows everyone why you are one of the smartest, brightest young professionals in the industry. So thank you for the work you're doing.
Thank you. It's a great honor to be recognized for that and to represent EREF as an award winner as well and support our industry. So thank you.
Awesome. Well, we'll celebrate you soon. So thank you to everyone who has watched. This concludes EREF Science Session on weighing the options, current strategies for managing PFAS and leachate. And although we may not have answered all of your questions, I hope you got a lot out of it. I know I, for one, got a lot out of it, and it was a very informed conversation. And Steph, thanks again for your time and expertise. And as a reminder to everyone out there, you'll be getting an email from EREF. It'll be through GoToWebinar, and it will have this recording, an evaluation, and a certificate of attendance. And again, that's coming early next week, March 1st. So please take a few minutes to complete that because it really helps EREF